Have you ever really thought about what it takes to run Facebook? I mean, the sheer, raw engineering power needed to make it feel instant for billions of people? Well, today, we're diving into the incredible story of how they took a simple open-source tool and pushed it to the absolute breaking point, and then went way, way beyond.
To really get a handle on this, you have to start with the numbers, and they're just mind-boggling. We're not talking millions of requests here. At its peak, Facebook's caching system handles over 1 billion requests per second. Just let that number sit for a second. 1 billion. Every single second.
And what are all those requests for? They're for data, an absolutely staggering amount of it. This system holds trillions of individual items in its memory. We're talking photos, statuses, comments, you name it. Trillions of them.
Which, leads us to the big question, the one that this entire explainer is about. How is that even possible? How do you build something that operates at that kind of speed and at that kind of scale, day after day?
Well, the answer starts with a tool that's actually surprisingly simple, Memcache. It's an open-source program that acts like a giant, shared, short-term memory for all of Facebook's servers. So instead of constantly bugging the slower database for info, a server first checks this super-fast cheat sheet. The whole system is based on this simple, three-step dance. Okay, first, a web server asks Memcache, hey, do you have this piece of data? If it's not there, and that's what we call a cache miss, the server has to go do the hard work and get it from the main database. But here's the magic trick. To make the next request way faster, it then saves a copy of that data back into Memcache. Simple, right?
But, a good idea is one thing. Making it work across thousands and thousands of servers, that's a whole different beast. And this brings us to the first major hurdle, scaling things out inside a single data center, where the engineers immediately crashed into the problems of latency and load.
So the first problem was basically a gigantic network traffic jam. Just picture it, thousands of web servers all trying to talk to thousands of Memcache servers, all at the same time. This all-to-all chatter created a massive bottleneck called in-cast congestion, and it slowed everything right down.
Their first big win was actually pretty straightforward. For just getting data, the simple GET requests, they switched up the protocols. Instead of using TCP, which is very careful and guarantees delivery, they used the much faster, leaner UDP. You can think of it like sending a postcard instead of a certified letter. It's just lighter with way less overhead. That one change, it cut latency by 20%, a huge win.
But, of course, fixing one problem just revealed a new one. What happens when a super popular piece of content, like a celebrity's viral post, gets updated? Well, its entry in the cache gets deleted. And suddenly you have thousands of servers all getting a cache miss for the same thing at the exact same time, and they all stampede the database at once. They gave it a perfect name, the Thundering Herd.
So, the next critical question became, how on earth do you stop a data stampede without your databases just completely falling over?
And the solution they came up with was just so clever. They created a system called leases. So, when a cache miss happens on one of these super popular items, Memcache gives a temporary token to just one server. It basically says, hey, you're in charge of getting the new data. And all the other thousands of servers, they're just told to chill out and wait a few milliseconds. And the results? Whoa. Just staggering. Before they had leases, a Thundering Herd could just hammer the database with 17,000 queries a second. With leases, that peak dropped all the way down to 1,300. That little token system totally saved their most critical resource from a catastrophic failure.
Okay, so they've managed to tame the chaos inside of a single cluster. But Facebook doesn't live in just one place, right? The next challenge was connecting multiple clusters within the same geographic region. And that introduced a whole new world of problems, mainly keeping everybody in sync.
So now the problem is all about consistency. You have data being cached in all these different separate clusters, but they're all reading from the same group of databases. So when a piece of data gets updated in the database, how do you make absolutely sure you delete the old, stale copy from every single one of those clusters?
They built the tool for this with a fantastic name, mcsqueal. Think of it like a little detective that lives on every database server. It's a program, an invalidation daemon, that literally watches every single change made to the database. It figures out which keys need to be deleted from the cache, and then broadcasts those delete commands out to every cluster in the entire region.
And they made it ruthlessly efficient. Instead of sending a separate network packet for every single little deletion, mcsqueal would batch them all together. This one optimization led to an 18-fold improvement, packing way more invalidations into every single packet flying across the network.
And now we get to the final frontier, going global. We're talking multiple, massive data centers spread across different continents. This is, without a doubt, the ultimate consistency challenge.
And here is where we meet the final boss, replication lag. This is where you run up against the laws of physics. When data gets written to the master database in, say, the United States, it takes real time, milliseconds, sometimes even seconds, for that change to get copied over to the replica database in Europe. The speed of light is a very real bottleneck.
This creates a really nasty race condition. I mean, how do you stop a user in Europe from reading old, stale data from their local cache, just because the update from the US hasn't physically arrived at their local database yet?
And the solution is another one of these wonderfully elegant tricks. They call them remote markers. When data is written in the US, a tiny little marker is immediately set in the European cache. If a server in Europe sees this marker, it's basically a little warning flag that says, hey, careful, the data you're about to read from your local database might be stale. To be safe, you should go ask the master database in the US directly.
So, after this whole incredible journey, from a single cluster to a truly global network, what are the big takeaways? What are the simple principles that you can pull from solving problems at this kind of unbelievable scale?
Well, looking back, 5 big lessons really stand out. First, separate your cache from your database. This let them scale each system totally independently. Second, you can't fix what you can't see. Monitoring was just as important as raw performance. Without it, they never would have even diagnosed the thundering herd. Third, they kept their web servers stateless. That meant they could innovate way faster, adding or removing servers without some big, complex coordination. And finally, through it all, they always came back to simplicity. The most powerful solutions, like leases and remote markers, weren't complex. They were just clever.
And this quote from the original engineering paper really just gets to the heart of their entire philosophy. It's a pragmatic trade-off. They're basically saying they are willing to sometimes show a user slightly old data for a split second if it means protecting their critical database systems from getting totally overwhelmed.
Which leaves us with one last, really fascinating question. After you solve for billions of requests per second and trillions of items, what does the next frontier of scale even look like? What challenges could possibly lie beyond this?